Oxidation numbers are kind of almost a bookkeeping technique that helps us balance oxidation reduction or redox reactions simpler and faster. Now, when we're doing oxidation numbers, we're essentially pretending that everything in the universe forever is ionic, and we can use ionic rules. Um, That's not the truth. We know it's not the truth. We know plenty of things in the world are covalent molecular compounds. But if down the hall in the physics department they can have frictionless ramps and ropes that don't stretch, then I figure we can make the occasional simplifying assumption just as well. Why would we want to do that? Well, take a look at this equation. And yes, if you really look at it, you can balance the atoms without too much trouble. There's 2 chromiums, that means there'd be 2 over here. There's 7 oxygens, so that's 7 H2Os. But the problem is that doesn't accurately balance the number of electrons moving around. And electrons have mass, so you can't balance an equation without also dealing with balancing the electrons. And inspection methods really only go so far. So when we're balancing redox, we're going to have a method to do that that follows through some certain steps. And really step number 1 is calculate oxidation numbers. The good news is this is something that just has a set of rules to follow. So any element in its standard state, that means any element the way I would expect to see it off the periodic table, iron, metal, oxygen, O2, gas, phosphorus as a powder, just P, then that has an oxidation number of 0. And remember, we're pretending everything is ionic and elements have no charge. That goes back to middle school. The atomic number is the number of protons, is the number of electrons. So an element by itself is neutral. It has an oxidation number of 0. Well, if I have a monoatomic ion, say I have a sodium ion and a chloride ion, then that's very simple. The oxidation number is the same as its charge. We don't have to pretend it's ionic. It is ionic. So if I have a barium ion, then the charge is 2 plus. If I have a sulfide ion, the charge is 2 minus. The oxidation number is 2 minus. When we have a compound or a polyatomic ion involved, we're going to have to do a little thinking about what goes on with the oxidation numbers here. But one thing we can look at is we can say that the more electronegative element should have the same charge as it would if it were an ion by itself. So making a rule, we can say fluorine, say the most electronegative element, is always going to be -1 in any compound. Oxidation number of oxygen is almost always -2. It is very rarely -1 in the case of peroxides. And it's usually fairly easy to identify a peroxide because it will be impossible for the formula to work if oxygen is -2. Probably the most familiar peroxide to most people is hydrogen peroxide, H2O2. And if we look at it in a minute, we'll kind of see how that is impossible unless the oxygen is -1. Hydrogen is just about always +1. Very rarely you'll find it as a hydride ion, and usually the way you find that is it's a binary compound with a metal. Here are the 2 important rules for compounds and polyatomic ions. For any compound, well, if we're pretending everything is ionic, then it has to follow the same rules as an ionic compound. The charges have to cancel in order for it to be something that exists. So the sum of the oxidation numbers in a compound has to be equal to 0. Think about, say, H2O. Okay? Well, if oxygen is -2 and hydrogen is +1. If I have H2O, I have 2 positive charges, 2 negative charges. So the sum of the oxidation numbers is 0. The sum of the oxidation numbers in a polyatomic ion, however, are not going to equal 0. It's going to be equal to the charge on the polyatomic ion. So let's see if we can apply this. Let's try writing the oxidation numbers of both of the elements in the permanganate ion, MnO4-. We can just kind of think through the steps here. So the sum of all the oxidation numbers has to be -1, because the rules say the sum of all oxidation numbers has to be equal to the charge on the polyatomic ion. So I don't know what the manganese is off the top of my head, but I do know that oxygen should be more electronegative. It's a nonmetal. And so it should have the same oxidation number as if it were an ion. So an oxygen, the oxygens there should be -2. That's the normal charge of an oxide ion. Well, there's 4 oxygens. So what's the total number of negative charges? Well, 4 times -2 would be -8. So I have a total of 8 negative charges. So now I need to think, what does this manganese have to be in order for it to total -1? Well, you could actually set this up as -8 plus x equals -1, but you'll see pretty quickly, I think, that the manganese has to be +7. -8 plus 7 equals -1. And this is the same process you would follow for any polyatomic ion. Well, what if I have a ionic compound? Let's say I want to find out what's going on with the chromium in sodium dichromate. And I gave you the formula here, Na2Cr2O7. And there's 2 ways I could do this. I could realize that the chromium is in dichromate. And so I could think, well, the dichromate ion is -2, and I need to have the Cr2s and O7s add up to -2 at the end, and basically ignore this sodium spectator ion. That bothers people sometimes. So let's look at doing it for the whole compound first. For the whole compound, sodium dichromate, which is a thing that exists, what do we know all of the oxidation numbers have to add up to on a neutral compound? Well, it's neutral, so it has to be 0. So now I can start thinking about the parts that I know. I know the oxidation number of oxygen. That's got to be the most electronegative thing in this whole set of 2 metals and a nonmetal. So the oxidation number for oxygen must be -2, which means what do I get for all of the oxygens? Well, 7 times -2 is, well, -14. So now I've got to find some place to get 14 positive charges to balance it out, because my sum has to be 0. Well, the sodium is there. The sodium is plus, and there are 2 sodiums. So I can take 14, and now I've got 2 positive charges here. So I guess I need another 12 positive charges. So the instinct is for people to go ahead and say, well, this chromium's +12. Don't do that. Why is that chromium not +12? Oh, right. For one thing, if something is +12, you've done something direly wrong. The highest theoretical oxidation number I've ever seen, and it's theoretical, is a platinum +10. There are 2 chromium atoms, so they're both going to give up electrons. So I can take those 12 positive charges and spread them out across the 2 chromiums. And each chromium must be +6. So let's do a quick example looking at it the other way, where we could just look at the polyatomic ion. And here is calcium oxalate, and I would like to know what the charge on calcium oxalate is. So I'd like to know what the carbons are, and I notice these 2 carbons are the same. So instead of dealing with all of this, I'm just going to deal with the oxalate. And if I just deal with the oxalate, the sum has to be -2. All of the oxygens, -2, -4, -6, -8. So in order to get a total of -2, I've got to have 6 positive charges spread out across the 2 carbons. So each carbon is +3. So follow these rules. A neutral compound must be equal to 0. Oxygen is almost always -2 unless it is actually impossible. And the sum of the oxidation numbers for a polyatomic ion must be equal to the charge. Here are a couple of very common examples that you'll see in redox reactions. You'll see permanganate going to Mn2+. Well, we said that the permanganate ion earlier is +7. So this is +7 going to +2. Do I have to add or lose electrons here to go from +7 to +2? Oh, right, I have to add 5 electrons. We can see oftentimes things going from oxalate to CO2. That's going to be really important when we think about this, that one oxalate ion makes 2 CO2s. You'll also see that down here with dichromate. Dichromate is orange going to the colorless Cr3+ ion. And one thing that people miss so many times is that a dichromate makes 2 Cr3+. So hopefully you can see, I did mention about H2O2. Remember I said I would say how this is utterly impossible if this isn't a peroxide? Well, hydrogen is +1. That's the only thing hydrogen can be. You can't have a +2 hydrogen because there's only one electron on hydrogen to begin with. So if it's H2, I have a total here of 2 positive charges. I really wish it would stop doing that. I have a total here of 2 positive charges. And so if I came over to here, I would have to balance that out with 2 O's. That if they were normally 2-, like they often are, then this compound would be impossible. It wouldn't end up being equal to 0. So what I then have to realize is, wait, this is impossible. I can't have this be 2+. This has to be 2- in order for this compound to exist. And if this is a total of 2 negative charges, then the peroxide here would have to be 1-. For example, you could have, say, like sodium peroxide, Na2O2, and again, you have the same issue here. Sodium is only +1, so it's impossible to get enough charges to balance it out if this was -2. It would have to be -1. So I can identify peroxides by finding the times that it is actually impossible for my compound to exist with a -2 charge on the oxygen.